All right, day 3, chapter 3, lesson 3, moving plates, measuring plate movement. We're on the back side of our piece of paper now. Capital MEA, SURING, measuring. Plate, capital PLATE. Movement, capital MOVE, MENT. Measuring plate movement. Deep oceans cover some tectonic plates. Other plates are made of large landmasses that are thousands of kilometers wide. How do scientists determine how fast these plates are moving? They observe Earth from the sky. Okay, so how can we figure out these big things are moving? Well, we have to use special technologies. One of the most successful types of technology for accurately measuring location is the Global Positioning System, GPS. As you read earlier, GPS is used to help create very accurate maps of Earth. Okay, so we know the plates are moving, PLATES, moving, MOVING. Global, capital GLOBAL, that means the globe or the entire Earth. Positioning, capital POSITIONING. Positioning. Position is where you are. So where you are in the globe or where you are on Earth. System, capital SYSTEM. And that's just a collection of things, like a collection of satellites, computers, and all kinds of other equipment. Over here, let's put open parentheses, capital G, capital P, capital S, close parentheses, equals. GPS consists of a network of satellites in orbit above Earth, as well as 5 ground-based stations. I'm guessing by now there are more than that. Working together as a system, the satellites transmit radio signals that can be used to accurately locate receivers on the ground. Okay, so you have, let's draw ourselves a little picture of the Earth, and we'll draw a little circle with 2 little squares coming out the side. We have satellites, SATELLITES, and then let's draw like these 2 little lines that come together at a point, and we'll put a little X on the ground, and then we'll call that, let's see, they say it's a ground-based station or a receiver, RECEIVER, receiver. So it receives a signal from the satellite. And then, if you have more than one satellite, you can measure the difference between those signals to figure out where you are. By measuring distances between specific points over time, scientists can measure how fast plates are moving. GPS data have recently confirmed that the African plate is moving north at a rate of 1 centimeter per year. So remember back on the previous page they said some can move up to 10 centimeters. The African plate is moving 1 centimeter per year, even slower than your fingernails. So capital AFRICAN, plate, capital PLATE, about 1 centimeter per year, 1 cm/yr. Slower, SLOWER, than, THAN, fingernails, FINGERNAILS. Okay, so what happens is you've got all these satellites out in space, and then you have like receivers on the ground. You can use all those satellites to figure out where you are, and then a year, 2 years, 3 years, 4 years, 5 years, however many years later, you measure it again, and it'll move just a little bit, and they can figure out how fast it's moving. In addition to satellites, scientists use ground-based radar and laser technology to directly measure plate movements. Using these technologies, the distance between 2 locations on different plates can be measured to within 1 centimeter or even less. By repeating the measurements, the rate of movement of the plates can be calculated. Okay, so as an example, let's say you have a plate coming in like this, and another plate where all the mountains are, and that plate is like that, right? And we know that these two plates are moving together to form those mountains. Okay, well, if you have a little receiver up here, and you have another one here, and they beam a little laser between them, you can measure that distance. And then, a year, 5 years, 10 years, however long, you'll notice that those are closer together. And then you can calculate how fast it's moving. Let's put, what are they saying? They're saying ground-based radar and lasers. So radar, R-A-D-A-R, and remember radar is basically sound. It's kind of like how dolphins communicate or whales can communicate. And then you also have lasers, which is light. Okay, that's everything here in the notes. Let's look at the pictures. Scientists are using GPS signals to measure the motions of tectonic plates. How else is this technology being used? Okay, well, looking at the picture, how do we use GPS? We make maps, and then we use maps. 10-15 years ago, you had these little units inside cars. People could buy it. It was called like a Garmin, for example, or a North Star or an OnStar. It would give you a little map, and it would help you drive around. Now this stuff is inside cell phones. Okay, why do scientists need advanced technology to measure plate movements? Oh, okay, there's a 6W question. Why? Why do they need all this stuff? Why would we want to measure the plates moving? Why would we want to know how far apart these points are? Why would we want to know how fast they're moving? Okay, well, let's think about this again, right? We can make maps. We can know distances, K-N-O-W, D-I-S-T-A-N-C-E-S. That helps us for travel, T-R-A-V-E-L. That helps us for shipping goods, S-H-I-P-P-I-N-G. Maybe that can help us plan when we're building buildings, right? Plan, P-L-A-N, building, B-U-I-L-D-I-N-G. For example, what if, along this fault, what if somebody needed to build a bridge that crosses over that? Well, you'd want to know how fast the plates are moving. If they're not moving at all, you could build a very solid bridge. But if they're moving pretty quickly, like this 10 centimeters every year, you'd have to figure out how to build a bridge that can allow the plates to move without splitting the bridge apart. All right. Now, let's double check these parts, and then tomorrow we'll do the annotating, highlighting, processing to make sure all that's in there and we're supporting the main idea. Continental crust is made of different kinds of rock than oceanic crust. Okay, do we have that? Oceans and continents. Continental crust is granitic, which is less dense. Oceanic crust is basaltic, which is more dense. Got it. As a result, continental crust is less dense and thicker than oceanic crust. Yep, the continental crust is denser, less dense. It makes it a little bit thicker. The oceanic crust is more dense. It makes it a little bit thinner. If it was too thick, then it would sink, and that would be a problem. Okay, you know what? Let's go back. Let's draw a picture of this. Okay, we're going to draw this here in oceans and continents because that's the section it was in. So let's draw like a bracket almost. Kind of matches that. Let's do like some little hashed lines. Let's call that the continental, C-O-N-T-I-N-E-N-T-A-L, crust, C-R-U-S-T. Then let's just draw like a thick line really thick. Okay, that is our oceanic, oceanic crust, crust. Okay, so this super thick chunk of stuff right here is the continental crust. That's the granitic. It's less dense. It's thicker. This line here is the oceanic crust. It's basaltic. It's more dense. So it's overall thinner. And then right here we can put waves for the ocean. Just kind of go over the word oceanic there. And eventually out here there's going to be a, you guessed it, mid, M-I-D, dash ocean, O-C-E-A-N, ridge, R-I-D-G-E. And then from this drawing you would be able to tell which way things are moving. So now we know it's moving that way. In fact, we can finish our convection currents. It's going to rise right up there by the mid-ocean ridge, but some of it's going to come over that way. Okay, let's check the next one. Convection currents in Earth's mantle drive tectonic plate motion. Okay, convection currents are in the Earth's mantle. They drive the circular path. They drive the motion of the tectonic plates. Very similar to what we drew here. According to one model, plates are dragged along like groceries on a conveyor belt. Dragged along. Yep, the currents drag the crust or the plates along. Tectonic plates move at an average rate of 10 centimeters per year. Flipping our paper over. Nope, it wasn't there. Where did we put that? Was it in slow motion? Millions of years, around 4 inches per year. Oh, okay, that 4 inches, that is the 10 centimeters per year. 10 centimeters. Put that in parentheses. Scientists use satellites, radar, and lasers to measure plate movement. We use satellites, radar, and lasers to measure the plates moving. Okay, everything is there. We'll be able to highlight and annotate it tomorrow. We'll highlight, annotate, process these things. Then we'll process by highlighting and annotating to make sure we're supporting the main idea. We'll find all the key details that support the main idea. All right, good job persevering with growth mindset. Roar Wildcats!